I think so. So we left off uh, last time on the depth-wise max pooling layers, understanding the depth-wise, the max pooling layers, the convolution layers, the implementation of how each uh, layer can be done in the Keras and TensorFlow framework. Uh, and we looked at the strides, the paddings, the features, the channels, the feature maps and the channels with respect to the layers and how they are connected. Now we will look at the CNN architectures. So generally, what here the author says is about the typical and a general CNN architecture in which we have a input image with the RGB channels, and we apply a layer of convolutions to it. Then the next is the pooling, then convolution, then pooling, then some sort of fully connected layers to get a latent representation here, uh, which can be used in the downstream tasks for our tasks that we need. Like you can use them for in the case of auto encoders or uh, classification or anything. So that was the use case. Now we talk about how we stack those layers and what are the activation functions that we mostly use. What are the common activation functions and the stacking that we have. So here they have given a representation of what actually happens in an intuitive sense with respect to how the images pass through those convolution and pooling layers. And the images get small and small as they progress through the networks. And deeper and deeper with the more feature maps. Feature maps, think of the feature maps here as the vertical and the horizontal lines or the circles or the high level features that we discussed last time. And this uh, regular feed forward network is added on top of it, and then the final layers of the prediction here in the end, if you can see my cursor. Yeah, here we have uh, final layers which produce our prediction, and the softmax that outputs the estimate of the class probabilities. So here in the end, we will have a softmax here, which will output the task probabilities if we are looking at the classification tasks. That was it here. Then we go down to the tip, in which they have convolution kernels that are too large. That's the rule of thumb that they're defined, and why they have those convolution kernels, convolution layers with the 5x5 kernels, and what's the difference between a large kernel and two layers with the 3x3 kernels. And it simply says that uh, those the 5x5, that's the large kernel, and uh, uh, the difference between the 5x5 large kernel and the two layers with the 3x3 kernel is that those 3 cross 3 will use a few parameters and will require a fewer computation and will perform better when stacked upon each. And this and they have also given us exception with respect to stride of 2 or more. If we use that, then that will reduce the spatial dimension of the image, and spatial dimension will represent in the feature maps that are not too sharp, and while the downstream task, if we are trying to use them in some sort of auto encoder or GANs, then those sharpness will be affected, and uh, because of the spatial dimensions of the image, and those information will be lost. And yeah, so that will represent a drawback in your how do I say it, the uh, FID, the metrics that you calculate in the end, and the convergence will be affected. And this is a simple CNN to tackle the fashion MNIST dataset that we have seen earlier in the chapter 10. This we have already done. If we go through this model, the first layer has this 64 large filters, 7 cross 7. Stride 1 because this. Then next we have a max pooling layer which pools the size of 2. This. And the spatial dimension factor by 2 because by default it will. And then we have a 128 layers twice with the 3 cross 3 filters with the activation of RELU and this. So this is how it goes. And here is the dropout with respect to this RELU. Sorry, the after the dense layer has been applied. And in the end, this is the softmax for the uh, class probabilities that has been used. This has been done to reduce overfitting on our training dataset. So these two dropouts that represent that are used here. And this then the author has defined the reachability of CNN over the accuracy of the CNN, that's over 92% here. And way to understand evolution of winning under this is under classical. And then we go on to the images that are used in these challenges. The ILSVRC ImageNet challenge that brought in the breakthrough in or the revolution in the deep CNN field. So they use this 256 cross 256 which at that time were sufficiently large images, and with respect to the 1,000 classes, the dataset that they had, and so that was the dataset that they had to compete on. Now we will go on to LeanNet 5. This was the first architecture that was introduced by Jan LeCun in 1998, and this was used for the handwriting digit recognition. And these are the layers, the 5 layers that has been shown here. So this is the first layer, the C1. That's the bottom-up diagram that we have, tabular, and input is the 32 cross 32 MNIST image, and here the maps is of 6 cross 6. These maps, C1, the 6, the 16. I'm literally trying to understand it. This in the left, if you can see here, uh, uh, these these are the maps, and this is the research paper that Jan Likun published in 1998. So I just opened it up, and this is the feature map, which I'm trying to understand of and how they are connected. What's the maps here with respect to here? Firstly, let's go through this architecture and then try to understand these maps. And then uh, in the S2, that's the name of the layer. This is the average pooling, which they have just the pooling here. Then this is the convolution with respect to the size of kernels. The image size will be, I think so, 10 cross 10, yes. And the kernel size is 5 cross 1 with the activation tangent. Then the average pooling layer with the size of 5 cross 5 and the kernel of 2 cross 2 and stride of 2. And this is the fifth convolution layer. And with this map, the size, this kernel size and the stride. And then this is the fully connected, which outputs a 84 dimensional vector. And the end in the end there is a RVF kernel that RVF layer that has the size of 10. That's the class probabilities. Uh, the which computes the equilibrium distance between the input vectors and the parameter vectors which we have given, which they have given. If you read this, it's a very beautiful document, research paper. If you read it, you will have a full idea of how these layers are connected and what was the thought process behind the initial uh, uh, in those good old days. What was how they thought and what's the intuition and how they came across this beautiful uh, uh, AlexNet this sorry LeanNet 5 architecture. So now let's get down to the maps that was which I was trying to understand. Uh, most these are some of the basic implementation details which they have used because of the padding. They are zero padded to the 32 cross 32 pixels and normalized before being fed to the network. Um, the rest of the network doesn't use any padding, so this is the size doesn't pass through the network. The image processes, sorry, through the network. The average pooling layers are more complex and they have a learnable coefficient 1 per map and adds a learnable bias term once per map and finally applies the activation function. So this is a three-step process in each average pooling layers. First, they calculate the mean, then multiply the results by a learnable coefficient, and then adds a learnable bias term again, and then finally applies the activation function. So this is the 3 or 4 step process that has to be done in each average pooling layer. And if we go to the C3 here, this is what they talk about in this table too, with respect to the maps that are connected to the neurons, and only 3 or 4 S2 maps instead of all the 6 S2 maps. So this is the table. So this I think so is the S2 map. 0 to 5 are the 6 S2 maps, and 0 to 15 are the 16 C3 maps. And how the neurons are connected here. They have described it here. Only 3 or 4 S2 maps. So each has, yeah. So they have given yep, I think so. In the 0 map, they have 3. In the first, they have 3. Second, they have 3. So 3, and then 3, then 3, then 4. And in the end, they are increasing it to fully 6 maps. Those connections. That I am a bit skeptical about of how they have and why they have increased this in this fashion. Yeah.
Hey, Mayank, before we
Yeah.
go on AlexNet, would you mind if I just made a comment or two on
Yep. Yeah.
this and also the what's called the little net that they first did with the Fashion Mist. It's Borstelman. Sorry to have him in here. Like responsibilities in life have been real, so I had to take care of those. But just really quickly, so we're looking at these, and these are like, the prototypic first, kind of nets that came out, and they usually follow like a conv pool, conv pool, conv pool. The first, the Fashion one, Mist one, deviates a little. It has 2 convs next to each other, and you can do that, and you'll talk about that in a second with AlexNet. But the whole big important thing for this is that, when you're putting these architectures together, one of the hardest things to do is to actually get the numbers kind of correctly so that the tensors, essentially flow from the one level to the next. And you have to be cognizant, about your tensor shape at each of those levels, because you want to have the same shape going in and the same shape coming out for your network to work. And that's one of the, just on a practical basis, that's one of the hardest things to do in my mind with TensorFlow. I mean, you have to be, very aware of that. And that's, when you use a pre-trained net, you kind of get out of that. But if you look at on page 461, the architectures, and that's this Fashion Mist simple CNN, or the little net, as it's sometimes called, you'll see that the depth, like you first start with 64 layers, in your Strata 7, then you double it to 128, and then when you go through the max pool, you double it again. And I haven't been here for a few weeks, so I don't know if you've covered that aspect already. But when you go through a max or like an average pool, you can double essentially, and that keeps the tensors the same. And then they get to flatten. And, it's kind of interesting that, with the 2 dense layers that are on the end, they go, fully connected layer 1, fully connected layer 2, and that's a dense layer in Keras. And then the final dense layer, which is the softmax layer, which isn't really the same thing. There was a paper out a few years ago that looked at this, and it was kind of interesting because the question, is really, well, how many layers do you need on the end? Okay. And I've never really found a satisfactory answer to that question. 2 seems to work really well, but it increases your parameter size. And because it increases your parameter size, these FC layers at the end actually really have a lot of memory. So the more layers you add at the end, the more memory you're going to eat up in your GPU. And you have to be cognizant of that because you may not be able to run your model. The, you know, it's a good place to add the dropout as well. But, you know, the paper I saw said that if you had 4 layers, you basically had a 99.7% chance of capturing almost everything that you needed to capture in those areas, with 1 layer being 75 and I think 2 layers being like somewhere like, you know, 85, 86%. So just
Mm.
an FYI there. And I'd love to know a better answer to this because I've never been able to figure it out, you know, what you're supposed to put at the end there. Um, you know, just, you know, we're talking, you know, we talk about strides and we talk about, you know, the kind of filters. These are older nets and they use, you know, large filters in 7x7. Remember that the original GPUs back in 2012, 2011, 2015 were low memory. I mean, 8 gigabytes in the 1080 T in the 1080 was a huge amount of memory and allowed people to do stuff. So, you know, that's one of the reasons why, you know, larger strides are used and people want to, you know, conserve memory. But the reality is that I think we've moved past that in practical application these days. Everybody is using like 3x3 comms or 1x1 comms, you know, a stride of 1 with a, you know, a small convolution. I don't really see people using these larger comms anymore, and they're not using them, you know, for practical purposes. Just a note on the Lenet. You know, obviously they're using average pooling because they probably hadn't figured out max pooling yet. And again, you know, you're using a 32 by 32 image because, well, that's all you know you really could fit, you know, on a CPU. Well, that didn't have the memory restraints, but, you know, still. And they were using tan functions because they hadn't invented the the ReLU yet. So I mean, you know, all these things are things you can try, you know, but generally, I think a lot of them have kind of fallen by the wayside. As when you discuss the nets, you'll see that by adding more layers or making the layers wider in the case of Inception, you get more functionality instead of just, you know, trying to mess with stride and, you know, all these things which are to a certain extent, you know, possibly just, you know, hyperparameter tuning. Okay, I will shut up now. Thank you very much.
Yep. Great points. Yeah, I totally agree with them. And they all the things that you said. I would just like to comment on the query that you had with respect to the number of layers that we use for in today's world. So in reinforcement learning, in the depth in the deep reinforcement learning, most of the Q networks that we sample that we use have a maximum of 4 to 5 layers, maximum of 4 to 5 deep CNN layers, which work in simulated environment. And if those I'm talking about those toy examples, which easily work. But yeah, if we go up to real 3D simulated environment like Calra, or some sort of which Calra, which is a fully GTA types. If Grand Theft Auto, if you guys know, it's a very cool game with respect to your simulating the real world. Not so real. It is in its own extreme, and there you can use some sort of a resnet with 30 or 50 layers that will work, because it will give you much more depth of the number of features that has to be learned by your input network. So there, those 50 layers that I have seen works. You do not need to go beyond that. Uh, and in the trivial cases of the toy examples, which we might see in the next chapters, these four layers easily work. So that was my comment on that. So let's now go to the AlexNet. Uh, AlexNet, they discovered, I think so. Uh, they were the first which discovered RELU, if I'm not mistaken, or was it in Inception? I'm a bit skeptical about that. Uh, so here they had uh, Uh, they were the first to stack the convolutional layers that directly on top of one another instead of stacking pooling layers on the top of each convolution layer, like they have done previously on the LinNet. And so these C5, C6, and C7 are stacked on top of each other. This is the RELU activation. That's the padding. And as uh, this is the 227 cross 227 image with the three channels RGB that is being inputted to this network. And we get this in the output, the glass is of 1,000. So this is the activation that's been applied in the end to get a class of to select a one of each from the output. And these are the middle layers. If we need to go into the number of parameters of each layers, then there is the paper. I think so. They have described it. AlexNet. If I have this, yeah, that's the AlexNet paper. And they introduced this local response normalization with respect to RELU. This I think so. It is given here too. Yep.
Can I just add one comment to everybody here? As Mike just pointed out, when you add inception layer, you get, I think, 6 for every inception layer. You get like 6 hyperparameters that you can now manually tune and so on. There's one company, there are a few different companies that allow you to, that provide tools for managing these hyperparameters. One popular one is weights and biases. Just want to throw a plug in there.
Yep. Yeah, totally agree. They have a great hyperparameter sweep as well, in which you can have your bounds, and it will sweep through them and give you the learning rate of those hyperparameters that can be easily utilized to reach the optimal result with respect to your network that you're using. So that,
Yeah.
yeah. So here, what they have done. So this was with respect to the local response normalization, which they have introduced in AlexNet. And this was one, how do I say it, seminal step that they used to distinguish their network from the rest to win this challenge. In I think so 2013 it was. They won it in 2010 12 by a large margin of 17%. Yeah. So between C1 and C3 layers, C1 and C3, they have introduced this SS2 and a max pooling of this with respect to the local response normalization. And this, what it does is encourages the feature maps to specialize and pushing apart and forcing them to have those wider range of features, which improves the generalization. And this is the formula for it. Uh, uh, these are the hyperparameters. If I go into the depth, this is the normalized output of the neuron that is located here with the feature map of I at the row U and V columns. And AI is the activation. After that, RELU step. But before that, and these are the hyperparameters. And you can go in the details in the research paper. They have beautifully explained the constants that they have used and the validation set, which they initially used to implement these uh, 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 mm, local.
Question.
Yeah.
Has anybody seen this their response normalization used elsewhere beyond AlexNet or in any currently used networks?
No, I haven't, but I'm wondering if it is. Kind of interesting. I think it maybe has been forgotten.
Yeah, there are some other normalization techniques that have been used.
Yeah, there's all kinds of layer norm and batch norm and but I haven't seen this used anywhere else that I'm aware of. So I was curious whether anybody else has seen it applied anywhere, or if it gave that much of a difference. But I haven't seen it used.
One of
So
the things
that's why I was curious.
One of the things about AlexNet is that AlexNet was really hinky because they had a split AlexNet across two GPUs. That's why if you ever see the diagram for AlexNet, it's like doubled, and it doesn't make sense. Like kind of like like there, it's almost like a doubled network where they have two different parts to it, and I wonder if the local response normalization was necessary to get that kind of working. I don't know, but I'm just telling you, it was definitely a hinky kind of. That's why you don't see it reproduced. People when people reproduce things, they start, they'll use VGG or they'll use Inceptions, but I've never seen AlexNet like really successfully reproduced.
I guess my feeling is that because Jeff Hinton was a co-author of the paper and he was all about trying to implement the brain, the processes in neurobiology into computer software, and this local response normalization is a biological phenomenon that apparently they find in neurobiology. So I think he was trying to implement that and maybe found that it helped. But yeah, I don't know what the history of it is, whether it's been used since AlexNet or not. But the fact that they've implemented it in TensorFlow and Keras must mean that people still use it.
Yeah, that's what I think so too. This is a local response normalization function, which Shri talked about earlier, which we can use it if we do a case search, maybe we can find some use cases of it in the networks that we have. And a variant of AlexNet, they have then defined ZFNet. I haven't looked into this, which won the 2013 ILSVRC challenge. And it's just essentially the AlexNet with few tweaked hyperparameters. So
I always thought VGG won that. You know, it was AlexNet won the first year, and then VGG won the next year, and then Inception won the year after that. They said ZNet, okay, but okay.
VGG was the runner-up to this in the 2014 challenge. The second place was by VGG. The first place was by this network, the ZFNet. That was developed by this these guys. So this is all for AlexNet. If you guys have any queries,
yeah, just that the local response normalization basically don't have any trainable parameters.
Yeah,
So that's the reason why. Oh, those are fixed parameters, right? I don't think you train them. Those are hyperparameters that you fix. The constants k, delta, o, beta, alpha, beta. Sorry. So they're not trained on the model. Whereas when you use batch norm or the other things, those are
that are
backdrop.
yeah. I think so. This some training examples produce this sort of inputs to. I do not know about this. I just read this earlier, but I didn't have much time to investigate. But yeah, since they run over the sum of the adjacent kernel maps at the spatial position of the total number of layers, it must be trainable. Or
no, Claron doesn't have any trainable parameters, whereas batch norm has.
yeah, batch norm
Like that is the as far when I looked into it, I remember that was kind of one of the main differences, and that's why I think one has fallen out of favor, because if anything can be trained, you probably have it trained than sitting and fixing things. I can't remember.
The parameters then would be very specific
finicky,
to the rest of
exactly.
the architecture. Yeah.
And
good point.
like one, I can't remember if there's something else where one basically looks at for across channels or something, whereas the other one, like with batch norm and layer norm and those things, you can just tweak that axis and then you can make it look through in different directions, right?
Yeah.
So, right.
Yeah.
And I don't know which was earlier. I think batch norm and layer norm and all those things came way past this, right? This is something I'm just, so I think that's why probably it's not there, not being used here. Yeah, that's pretty much.
Cool. So let's move to the GoogleNet, which was the Inception, which was made possible by the subnetworks.
Sorry, Mayank. Just one more question, actually. With the data augmentation, I think somewhere in the end, there is a mention of the last line. Somewhere he talks about noise, right? Adding white noise. Yeah. Just
adding white noise too.
Yeah, exactly. And yeah, I kind of figure that since it's white noise, it's not learnable. But don't a lot of augmentations add in like caution noise, basically, if you even look at cutout and those kind of things, that is kind of adding random noise, right? So I was just kind of having a disconnect between both those. Or is that noise that they're adding purely just for like the regularization aspect of it?
Regularization.
So there is nothing to do with the data augmentation in that? Because I mean, it's implemented in argumentations and all those, which are augmentation libraries.
So for image augmentation, my understanding of, when you're adding noise, okay, you're trying to target different functions. And for me, it's more like what are the different parameters you can tweak? So, he shows tweaking the, physical location, the orientation, the zooming, and the rotation, skewing, flipping, things like that in that picture. But you can also tweak your brightness, your pixel range. You can tweak a lot of other parameters. And I think that the more non-random noises that you can add could help with that. Again, the bottom line is that there are two ways to think of augmentation. You can think of augmentation first and foremost as a regularizer, and that's, I think, how Jeremy Howard uses it. When you run through a gazillion examples of just random flips, rotates, crops, zooms, skews, and just run it to infinity. Okay, when you're doing that, you're actually you're regularizing. Okay, and that's well described in the literature, at least from the people I think that know the most about this. Conversely, when you are choosing specific augmentations that have either a real world analog or kind of are going to work better, then it's different. It's almost like providing additional cases. Dan Saresian in Schmidhuber's lab had a really early paper, which is one of the first uses of data augmentation outside of the MNIST data set, where he took galaxies and he rotated them 90 degrees to get 4 galaxies from one galaxy. Well, that makes sense because the orientation can be in the sky, well, it can be anything. So that made a lot of sense to do, and that improved his classifier, not necessarily strictly on the basis of regularization, but on the basis of actually providing additional training examples. Okay, so there's an art to it. If on the first part, on the second part, it's just kind of a regularization function. So
Stephen, so what you said is that there's 2 ways in which augmentation works. One is it extends your training set to examples that you might possibly encounter in the real world, like you're talking about rotating galaxies and so on, because galaxies can be found in any rotation, in any orientation. So that's what I understood it to mean. Now you're also talking about a regularization aspect. I don't really understand what you mean by that. Yeah. So could you explain a little bit more what you mean about how
sure.
it functions as a regularization?
Sure. So this has been described by Christopher Rhee at Stanford and his group. And what happens is that normally when you have a data set, right, and your data set is small, the CNN is power hungry, you want more cases, all right? So you're going to augment. But if you start augmenting willy-nilly, okay, you'll find that certain augments work, certain augments don't work, okay? Those augments that don't work, I think actually some of those actually become adversarials, where they're actually going and decreasing the accuracy of your training data set, okay, because they're opposing what you did. If you were to take, like, for example, consider like a chest x-ray, all right? If you have normal chest x-rays, and then I flip that chest x-ray upside down so that the neck is at the bottom of the picture, right? Well, that doesn't make sense, okay? So what happens is that in the right setting, you could actually decrease your classifier performance by feeding it wrong information.
Right.
Okay. So you say, okay, well, I'm not going to do that. Well, actually, if you follow Jeremy Howard's, approach, he does that and it works. Well, why is that? The reason is that you're giving the CNN, okay, not like just another 100 or 1,000 examples. You're giving it like 200,000 or 300,000 examples of all these different possibilities, right? So it starts to make the CNN forget things, right? And that's what you want a regularizer to do, correct? You want the regularizer to forget, and to broaden, just remember the important stuff, forget the other stuff, and broaden my response to new data. So that's how it can function as a regularizer.
I'm not sure does Jeremy really advocate putting in upside down chest x-rays? I thought,
No,
I mean,
I don't
in
think
his
left,
discussion,
left, right.
When you look at image data augmenter, when you look at the Keras image data augmenter, okay, I mean, I'm not trying to put words in Jeremy's mouth, but I know that Jeremy, at least the last time I, looked at his stuff on this, which I admit has been quite a while, years, okay? But the last time I looked at this, okay, Jeremy was like, put it all through, lots of different augmentations, run it to heck, and, even augment your test cases, test time augmentation. So that is why the regularization effect comes in.
well, what I remember about Jeremy is he said, you got to think about, when you do augmentations, you got to think about it. If you're looking at pictures taken by a camera, you never want to flip upside down because that doesn't make sense. You're never going to encounter those cases. People always stand upright when they're taking pictures. And so, you have to do augmentations that make sense. You don't want to rotate your pictures 90 degrees because nobody takes pictures at 90 degrees when you're, what I understood augmentation is I understood that it has the effect of regularization because it makes you robust to changes in your images. Like by taking different flips and so on, you're basically increasing your number of training examples. By taking different shifts, you're doing the same thing. By doing different contrasts, you're basically making yourself robust to all kinds of different cases that might occur. And that, in a broad sense, is a regularizer. But the main thing that image augmentation does, as far as I know, is just basically extend your training set.
I guess I got to post the paper. It helps. It helps to extend the training set, but I think that most of the time it functions more. I think it functions more as a regularizer, and I like the science behind that I can provide for you. Okay.
Okay, that'd be great.
I'll post a link to the paper.
Okay, wonderful.
Yeah, just to add to this discussion, if you guys look at the self-supervised learning techniques that are coming in with respect to the contrastive objectives in the seminal papers of CMCLR, MOCO, and REST, which will be there in NeurIPS that starts on the second week of December. There, they have used these argumentations for increasing their self-supervised classifications with respect to increasing it by the number of samples as you guys just said, and the number of, how do I say it, there are basically two classes of argumentations that we can define. One is the classic and the standard. That's the flip, the translation, the scaling, and all. Then the next set, that's the more advanced, can be the strong argumentations, can be your cutout, your auto argumentation policies with respect to randomly having some sort of sharing, translation, and rotation on the same image. And there are derivatives of that which they have used in the papers that I've just described with respect to CLR and MOCO and the derivatives of it, and where they have specifically improved their training accuracy and those classification objectives, the contrastive objectives with those simple, not simple, but those strong argumentation techniques. So if you would like
Are
to...
you, so are you
yeah.
saying albumentation? I'm not sure what that word you're saying is. Is it albumentation?
No, it's argumentation. That's the data argumentation.
Oh, data augmentation. That's what you're saying. I see. Okay. Yeah. Sorry.
So this is, that's the same paper, the first version of the data augmentation policies that they have just... So going back to GoogleNet, this was the Inception modules which allowed us to, how do I say that? That was the seminal notation that the Inception modules were a breakthrough, which use the parameters more efficiently than those previous architectures, and the number of parameters were reduced drastically since they applied all the convolutional layers applied this ReLU activation function, which dropped off those neurons. So the parameters were less. Here in the figure 14.13, this Inception module has been defined. Let's start from the bottom. Here they have two convolution layers of 1 cross 1 plus 1 is the stripe, and then this is the max pool layer, which they have inputted it to the convolution here, 1 cross 1, this 5 cross 5, and this 3 cross 3, and then they have concatenated it. And these, how do I say it? This module is being replicated and being reused across the network multiple times to give that sort of abstraction to those layers. And
a question with that module. Why is the last one you have a max pool followed by a 1 by 1? Does it make a difference if you have a 1 by 1 followed by a max pool?
Here in the paper,
right.
Because they have this was a naive version in which firstly they have tried this, and then they had used this 3 cross 3 max pool, then followed by the 1 cross 1 convolution.
Right.
And this worked, but I do not have any idea about why a max pool followed by 1x1 works, and why 1x1, because they have if we look at it from a naive perspective, these 1x1 wouldn't be able to capture much features, because they will just output the same. Uh,
They'll
Previous
only
layer,
be across
yeah.
the channel rather than doing it across width and height. The only reason why I was kind of bringing this question up was the way they have used 1x1s for the previous two branches is basically for computation, right? You want to reduce computation, so that's why you do that. Or if you look at that left paper that you've suggested, moving from A to V was basically for reducing the number of computations. So if you stick that 1x1 actually before that max pool, that should inherently reduce number of computations even more. That's why I was kind of confused if I was missing something, or is there any other insight someone has?
Yep, that's what is written here too. If you can see the highlighted text.
Right, to reduce the computations, right? Yeah.
The only comment I would make is that if you think about the 1x1 kernel acting on all the the stacked features in the depth rather than across, it almost works a little bit like an instance norm, but you have a reduction in dimensionality with the 1x1 convolution, and the instance norm you don't. I don't think anyway. Kind of an interesting parallel if you are familiar with the instance norm.
Yep, maybe. So, any comments on that?
About why convolution is next to max pool, that's just my guess. I don't know really, but I think max pooling is destructive in terms like any pooling is it destroys some information, right? And maybe this combination would preserve less information if you do it otherwise. But that's my guess.
Cool. Okay.
Yep. Because these 1x1 and 3x3, the way that they have implemented here, they these middle layers actually gather these two layers actually gather more features, as I can imagine with and this is for lowering the computation, and this on the right, the max pool followed by the convolution is also used for the compute reductions. So before these expensive middle, how do I say it, this vertically stacked middle layers come into the picture. So that's what this Inception module is trying to balance, if I'm not wrong.
Just to clarify something, Arto, you're saying max pool is destructive, which I understand. So doesn't that support the argument that your destructive should come towards the end rather than towards the beginning?
Yeah, I follow that. I follow what you're saying, Riku.
Yep.
I think technically the max pool is coming after the previous layer. So, you've had a conv output where that depth concat is, it's feeding into the same thing as feeding into the next inception layer. So the max pool is there. The only thing I'm kind of like looking at this and thinking to myself, because max pool, kind of changes the number of depth. I would have to look at the inception, but the
max pool doesn't change the depth, right? It'll only change height and width.
But it changes the tense. The
1x1 will change the depth. The max pool.
The 1x1 will change the depth, right?
Right, not the max pool. The max pool will just change height and width, right?
Right. It's going to change the height and the width. So the only thing I'm trying to reconcile in my mind is we have a 1x1 convolution in each of those pathways, each of the 4 pathways.
Right.
So we know that we're going to have, the effect of a bottleneck. But if the max pool is creating a bottleneck itself, is that 1x1 convolution
But the max pool is not doing a bottleneck, right? It's not going to be changing the depth.
It's not going to change the depth, but it's going to change the width.
Or that way, even convolution will change the width, right? And first of all, you're not changing the width here because otherwise you can't concatenate. You have to keep the same height and width.
Keep everything same. That's why I'm just
for it to concat. Yeah.
Wondering if the convolution is it's a little bit different on that one. I would have to look at the network. Don't know.
Cool. Okay. Yeah. Just curious.
One interesting thing to note, just by way of before we leave that diagram, can you scroll back up a bit, Mike? Before we leave that diagram, to notice that the left-hand convolution, the left-hand 1x1 is really like is a skip connection. It's preserving. It's not exactly preserving, but it's kind of preserving the information that's coming in. Anyway,
right, it's more of a linear combination across the depth of what is coming in. Right.
That's
yeah.
right. That's right.
Sorry, guys. A naive question. Why do you think the convolution layer is doing something to the depth? So the depth we're talking about is the stack of all the channels, or is there something else you guys are referring to?
Yes. So the convolution 1x1 basically is going to operate just on 1 pixel, right? So the operation is basically on the depth that is happening. So if you come in with like 28 by 28 by 256 filters, you'll pass it through a 1x1 conv, and that'll be something like 1x1 by 64, let's say. So your output, if the padding is same, would have changed from 28 by 28 by 256 to like 28 by 28 to 64. So your 256 depth channels have been kind of linearly somehow combined with learnable parameters to like 64 channels, right? That's what the 1x1 called.
Where did I thought the convolution, all that it was applied itself only to a single layer. It was the operation among different layers was what was a different operation. That was like a depth type. But so is this convolution a depth type convolution then?
So the 1x1 convolution basically doesn't do anything on height and width, right? Because it's just 1x1. So it's just looking at 1 pixel. So the operation that is happening is on the depth axis.
Okay, that was my misunderstanding. I hadn't understood that's what that 1x1 plus 1s was actually referring to.
Right. Yeah. So in general, that they call it multiple things, right? Network in network, bottleneck, like Stephen was saying, or 1x1 convs. They basically operate on linearly combine the depth axis. That's what it is.
For Rekil's max pool question, I'm not sure, but I had one idea. Like in the before in pre deep learning days, when we had something like a wavelet transform, right? We would always subsample the images so you can get information at different scales. And I think they might have. Yeah, they might have got inspiration from those ideas, like, because this allows you to subsample. What's confusing me is like the first one, there's 1x1, 1x1, and 3x3, and how are they still able to do the depth concat at the end? Say you start with say 128, and the max pool will reduce it by size of 3, right?
No, the max pool doesn't reduce it. It's a stride of 1. So all it's doing is taking averages of a 3x3 pixels and just replacing every pixel with the average. So it's not changing the size.
There is padding. There is padding here. It's a different, yeah. It's not the conventional max pool where you just do like a 2x2 pool and then that would reduce it to 1 pixel. Here there is inherent padding that happens. So at the end of the day, everything will be the same on the height and width dimensions. That's why you can concatenate.
Okay, thanks.
But yeah, I think what you're saying makes sense. Like the 1x1 is for reducing computation, but here I think, yeah, okay. So it's kind of like this different scales that they're trying to pull into picture. Okay.
Yeah, I think long back there was some intuitive explanation of this. If I find it, I'll share it in the Slack channel.
Cool. Yep, sounds good.
Oh, good.
So now let's look at the architecture of this CNN with the number of feature maps, the kernel sizes. So here, the input is a. Should I go step by step, or because there is an interesting figure in this paper, yeah, where they have used this. If you guys can see this, that's the same thing. Just that this is the Inception modules 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are the 9 Inception modules that they have used along this path that they have taken. This is, I think so, for the number of layers that they have is this is Inception net the bells and whistles. I was just trying to look at the number of layers that they have. Is it approximately 20 or something, or what was because they haven't mentioned it here. If we give in the model some summary, so anyways, we can get to that later. This is on the book is the diagram with respect to these layers and how they are inputting and the flow of information between each of the layers along with the Inception modules. And we can take a detailed look at it with the number of channels, the image sizes, and the layers of. So here, if we go to the text, it's a bit easier. These divide the first 2 layers divide the image height by the height and the width by 4. These two layers. So the with respect to the area, that's divided by 16. The cumulative part of these two layers to reduce the computational load. And first layer, this uses a 7x7 so that the kernel, the information is preserved. Then the local response layer from the previous learns a wide variety of features. And then these 2 convolution layers that we have that are stacked, where the first acts like a bottleneck layer, which is trying to limit the information and the features that are flowing through your network. Then there is a local norm layer, local response norm, which capture a wide variety of patterns. Then the max pool, which reduces it by 2. I think so. Yep, to speed up the computation. Yeah, and then there are the 9 stack of Inception modules. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, and these have a couple of max pool layers to reduce those image height and width, and to just speed up the computations. And then there's a global average pool. This is important here because this global average pool layer, which has a vector of 1024, has means of the feature map, and this what it does is try to in the classification task. It does not matter where the object is, but uh, uh, how do I describe it?
To be spatially invariant, right? That's what.
Yeah,
right.
yeah. So these are spatially invariant, and they try to reduce those dimensions, and the number of parameters are reduced to limit the overfitting. And then there's a normal dropout with the 40% rate, and the fully connected 1000 units, and then the softmax to select those classes. So this is it for the Google Net
And then for
architecture.
the just a quick question in that for those 9 Inception modules, those 6 numbers are just the 6 numbers represent the 6 convolution things, right? In the Inception module.
Yep.
Those 6.
Yeah, on figure 1413, there's those blue boxes.
Yeah.
Those are the hyperparameters that represent those blue boxes, the number of kernels for each of the blue boxes.
Oh, got it. Thank you. Yeah.
Yeah. So that's
one more point. Sorry, Mike, with the global average pool, that is what kind of gives you the ability to run any of these models on any image sizes. Previously, when we had like AlexNet and the previous, even the LeNetNet architecture, which you showed, if you don't have a global average pool at the end, when you end up with a fully connected network there, that fully connected network has a specific size, which is dependent on your input image size. So that's why all those architectures had like a fixed image size that it could be run on. But CNNs in theory like shouldn't be dependent on the image size since it's just a bunch of filters that you're applying. The problem was this connection, this last connection, when you try to flatten and try to connect it to your fully connected layers, that's where it would break if the sizes were different. So that's what like the global average pool or any of these adaptive average pools kind of sort that out by predetermining what size that should be. That was an interesting point that I was reading.
Yeah, that's a great point. Like, so the max pool is like 3 by 3. I forgot the definition of the global average pool.
You basically break that whole feature map into one single value, take the average. So 1024 basically means that on the depth axis, you have 1024, which is going to be a constant, irrespective of image size. Your height and width will change depending on your image size. But because you're doing a global average pool, it doesn't make a difference, right? Whatever the size be, 4 by 4, 10 by 10, 15 by 16, you're just taking an average of each feature map and slamming that into one value.
Okay. Okay, great. Thank you.
There was kind of like a movement about, I don't know, maybe a year and a half, 2 years ago when I was reading, people got really excited, by going back to average pooling and global average pooling, over max pooling. And then I think we kind of got distracted with transformers and GANs. Has anybody heard anything more on that? I don't think that's settled yet, is it?
from what I know and what I think from Jeremy's course is that Maxpool is kind of lost favor now because you can kind of inherently get that with stride and convolution.
Right.
If you just dump by stride too. So why do you're doing more computation if you do convolution on the whole thing and then do a Maxpool? Whereas you can just do stride to convolution. It's lesser number of computations. And the latest more frequent, I think even with ResNet and all, you don't see that. I mean, towards the end, you probably may have a Maxpool or when you want to change the size specifically, but yeah, from what I have seen, like Maxpool's kind of lost favor.
Yeah, that's what I perceived.
Doesn't
Thank you.
Jeremy concatenate a couple of
Right.
different poolings?
Yep.
I forget which
I think
one.
he does max pool and average pool. He concatenates that towards the end for the classifications. So here, if you had 1024, he would concatenate max pool and average pool. So you'd end up with like 2048 channels there on the depth axis.
Cool.
So the adaptive average pool does the adaptive part with respect to the height and width?
Yes, adaptive, basically you specify what height and width you want. So you can think of it in two ways, right? Global average pool, you know that you know the certain number of channels that you want, so you fix that aspect of it.
Right.
In average pool, if you do if you do adaptive average pool, that is still going to be like a 3D block, right? You're going to have height, width, and depth. But if you have to connect this to a fully connected layer, you have to flatten it at some point.
Right.
So even if you have an adaptive average pool, you will specify what the H and W is. So let's say 5 by 5. So anything that comes before that at any size in the convolutions, you want to map it down to a 5 by 5. That's how that is done. And now you know it's 5 by 5 by a certain depth. So 25D needs to get mapped to that specific fully connected layer, which is, again, deterministic. So again, it'll work for any image, any given input.
Any size of the
image. Right.
That makes sense. Thanks.
Yeah.
Cool. So cool. So these networks are still being utilized nowadays at the inceptions with respect to I think so version 3 and version 4 along with ResNets and VGGs are more popular. Yeah, but let's try to quickly go down there. So here they describe the loss in the empirical formulations, which they have scaled it down by 70% to how do I say it, to make it computationally feasible. And the goal was to fight the gradients, the vanishing gradients problem, and to regularize this network, which I think so was a part of their intuition as to why they are trying to develop this these layered architecture. So. But they have also mentioned that afterwards that what they were trying to intuitively imagine was that their impact had much less as compared to what they initially thought it would be with respect to the scaling down of the overall loss and fighting the vanishing gradients problem and regularization of the network. So this is with respect to the Inception V1 or the GoogleNet as they describe it. So there is Inception V3 and V4 too. It's an intriguing read. I will recommend everyone to go read the research papers and try to take in the intuition behind them and how they improved it. Next, we will move on to the VGGNet. This was the runner-up here in this ILS-VRC challenge. And it's a very simple layer with 2 or 3 convolutional layers and a pooling layer, and then those 3 convolutional layers and a pooling layer stacked together, and so on, with just of 16 or 19 layers, depending on the variant. And the final dense with the 2 hidden and an output layer using only the 3x3 filters that are there. If I had this paper, yeah, I will give a quick overview of, yeah, this is the VGG16, and this is the VGG19. This is how they have defined it. These are, if you guys can see the screen, so this my Mendeley desktop.
Yeah, we can see.
Yeah, so these are the 16 weighted layers with respect to the con3. The input, these 2 layers are stacked. Then there's a max pool, then these two layers, then max pool, then these 3 layers, then max pool, then these 3. Yeah, max pool. And then this is a fully, then max pool and the 2 fully connected layers of 4096 each. And then fully connected dense layer of 1000, which has the class label information, followed by the softmax activation. So this is VGG16, and similarly there's a VGG19, which we use nowadays for the basic tasks. If we are trying to set up a baseline, these are the first, I think so, networks that we look at, and then we take it from there. So this was from my side. If anybody has any questions or would like to contribute, please feel free.
It's just interesting that VGGNet is so much simpler. There's no 1x1s. It's all just serial combinations of things, nothing stacking side by side. It's just much simpler, and it gets a better result. So that's kind of what stood out to me. It gets a better result than Inception, I guess.
Yeah, but having personally experimented an awful lot with VGG, it's limited, number one. Number two, the big problem with VGG is that you really just can't keep expanding it. You know, I mean, and you start to suffer, you know, for the parameters. The relative power you get with a ResNet over a VGG net is substantial. I mean, a VGG is great. It's a go-to network that you can get good performance on, but you can get better with other networks. Like the Inception ResNet variants are actually rather nice, just as an aside.
Yep, totally agree. These are the classical architectures that we are studying to, how do I say it, to get an intuitive feel of how the next gen architecture should be implemented. Yeah, we can use them, and because these are classics, so they will never go out of fashion. But yeah, those new architectures are coming in every day, and specifically with respect to AutoML, in which you define those bounds, and based on your throughput and latency, your architecture is automatically selected. So that's how we do it nowadays. But yeah, these uh, are the classics that have to be kept in mind. To like these are the history. This was published as a conference paper in ICLR 2015, and just in 2020 you can see this is ancient history. So I look at it from that perspective, that you have to know the history to understand in which way our machine learning literature is heading towards, and the future, and how it will be shaped. So that was my 2 cents, kind of.
Yeah, just to add to Joseph's thing, like this is a simple architecture, and like basically what we keep studying after this is just stacking more and more layers primarily till you get diminishing returns with a few tweaks here and there. But yeah, like stacking convolutions is basically the essence of this whole thing there.
I just posted a link to Papers with Code has a really nice page on the ImageNet, on the history of ImageNet and where we are now. So it takes you all the way up to now. It's kind of interesting.
Yeah, to Rekil's point, I think the key is, if from at least the history and stuff, is to understand, the base capabilities or that were introduced and then carried forward and modified. So I think that's what you learn by going through these, is what are the basic techniques that get applied repeatedly.
Yeah. Because in today's world of AutoML, those neural architecture search, AutoML and neural architecture search, these basic techniques are being utilized to get to those, how do I say, those end parameters of throughput and latency requirements that we want. Suppose in the edge devices or in the mobile space, that's those specific areas, those networks are being converged to. And these are the classics and the basics that we need to have command over to get to that point. So yeah, totally agree.
Yeah, it's just interesting that in the Papers with Code website, the VGG 19 is number 184 on the on the list of performance. So there's a lot that's happened since then.
Yeah.
It's almost like 10% difference, right, in the accuracy management. That's how much they push through it.
And plus with the 144 million parameters too.
Right.
That's very much high.
Trade-off, right? Yep.
That's
You're deploying it on a phone or something. There's always how much accuracy versus how much memory you actually have versus latency also.
Yeah. So that's cool. So that's it from my side. The next time we will pick up on ResNets. We'll discuss ResNets and go through SE nets and trying to implement this in Keras. And yep, we'll take it away from there.
All right. Everybody have a good week.
Yeah. Thanks, everyone.
Thank you.
Okay, I guess we'll see you next week.
Yeah, next Sunday?
Yeah.
Cool. And happy Thanksgiving and enjoy, guys.
Thank you.
Thank you. That's cool of you.